Good afternoon, everyone, and welcome to today's AMPC webinar on the Aggregated Waste to Energy project. This project is now completed, and we're lucky enough to have Max and Gareth from All Energy to talk about the project, as well as Matt Deegan, who is the Sustainability Manager for AMPC here. So Matt's actually going to introduce the program, but just before he does, for those that are new to this system, the GoToWebinar, if you've got a question, we really encourage you to go to the question tab on your toolbar, type your question in, and then throughout the presentation, we'll be asking questions to the relevant presenters. So want to try and make this as interactive as we can, so please feel free to add the questions. At the end of it, we will also have another space for questions, but we'll try and sort of filter them throughout the time. So Matt, I might hand over to you so you can give a bit of a background and briefing on the project. Thanks very much.
Thanks, Amanda. Welcome everyone to the Aggregated Waste to Energy webinar on a project completion. I'll just run through the reason for the project and the basic outputs of the project before handing over to Max Barnes and Gareth Ford from All Energy, who were the project providers. So I'll just give you some background as to why this project is particularly relevant for red meat processors. So the Aggregated Waste to Energy project investigated the techno-economic feasibility for red meat processors to combine waste to energy processes from their own communities and supply chains, reducing fossil fuel consumption. And the key word being aggregated. Why did we put that in there? Because a lot of red meat processors have found in the past, when they've looked at investments into waste to energy, that they've had insufficient scale on their wastes to justify the expense of investment in waste to energy. So therefore, this project looks at combining wastes or aggregating wastes from red meat processors and their communities. In other words, their communities that consist of local councils, adjacent businesses, or other providers of agricultural or primary industry wastes. So the webinar will be presented by Gareth Ford and Max Barnes of All Energy. And the project looked at a circular economy approach as far as making aggregated waste to energy more feasible in regional locations. It looked at both a regional value chain that included a red meat processing plant, an adjacent piggery, and interested local councils as far as the aggregated waste is concerned. And secondly, it looked at a red meat value chain, including a red meat processing plant, a feedlot, and with access to residual wastes from adjacent agricultural activity. So just a brief intro to All Energy. They're based in Brisbane. They provide a high-level energy strategy and process engineering consultancy. They have been working with red meat processors for over a decade, so lots of experience in the red meat industry and particular experience in complex brownfields process, integration, embedded generation, energy efficiency, energy strategy and management, and renewable thermal power and hydrogen solutions. So I'd now like to hand over to Max.
Thanks, Matt. Amanda. Yeah, all right. So hopefully everyone can see this opening PowerPoint slide now. As Matt mentioned, we were looking at aggregating waste to improve the performance and also the economics of anaerobic digestion and biomass combustion were the two waste to energy technologies which came out on top. So the objectives of this were providing a bit more clarity on those key parameters that impact the economic and the technical viability of waste to energy, and also mapping out those options and collaborations for facilities, whether that be with adjacent businesses, other agribusiness operators or the local council of the local government area that they're in. So we did 2 specific feasibility studies on 2 specific case studies, and we also created a tool to assess the thermal and electrical energy potential from your own waste streams, and a brief concept feasibility, and I'll go through that at the end. So in terms of the site selection, we sent out an expression of interest to processors to assess the capacity to report data, what kind of sub-metering and what kind of waste management practices are already in place, and also what thermal fuels, what are you paying for them, what's your power, what are you paying for that. And then so we compared those with a weighted criteria matrix to select the test sites. So a few of the questions we were looking at, as I mentioned, were tonnes hot standard carcass weight throughput, approximate production of the following non-recyclable waste, so things like paunch, DAF sludge, waste activated sludge, green stream screenings, red stream screenings, manure, and then just general kitchen cafeteria waste and contaminated plastics and contaminated cardboard. We're looking at what kind of thermal loads are on site, what kind of electrical loads are on site, what kind of fuel you're burning, and then the cost for those. So the long list of the technology options that we, just based on previous works that have been a good fit for the red meat industry, anaerobic digestion of organics to biogas for power. So you'd be digesting your on-site organics plus any sort of adjacent waste that you might have, or the food organics, green organics is that FOGO acronym there from the municipal solid waste. Co-firing of wood chip with paunch or other biomasses for processed steam in either a processor or a feedlot. And we also briefly considered gasification of RDF, which is refuse-derived fuel. So that's things like packaging, plastics, wood, etc., from your municipal solid waste. However, as Matt really alluded to at the start, the economics for that one really need to be bigger, more than you can sort of realistically achieve in a red meat processor plus other wastes. So these are just a few example anaerobic digestion plants that are operating around the country. So these are a few examples of the CSTR, continuously stirred tank reactor style, which you may or may not be familiar with, the alternative of CALs, covered anaerobic lagoons, which is obviously a lot more common in the red meat industry. But this one gives a lot more control over those operational parameters like mixing and temperature and microdosing of oxygen to control your sulfide gases, and also for that reason permits a higher total solids percentage as well. So just the general benefits of investing in sort of waste to energy projects for your own plant would be reducing your power costs, which both that KVA, the demand charge, and the kilowatt hours, the volume charge, reducing your thermal energy costs, waste disposal costs. This is getting to be a big one now, improving your environmental outcomes and your social license to operate, and also reliance on the outside fuels. So you have more of that control over creating the fuels within your own boundary and less reliance on international supply chains and someone else delivering your fuels and your power to you. And so with that comes a reduction in Scope 1 and Scope 2 emissions, and with anaerobic digestion in particular, you can concentrate those NPK nutrients for a soil condition or a composting or even just general irrigation. So the methodology we followed, we went out to site, took a bunch of samples. So just looking at the top right here, going along the top, we took dewatered paunch, we took blood from a piggery, guts from a piggery as well. So due to the African swine fever, there's been less of a demand in the market for rendered porcine products. So people are really exploring what are their other options with this waste that might not be able to be rendered anymore. In the top right, there's yard wash water, so things like belly wash and just washing down the manure from the pens. At the bottom there, there's save-all overflow. There's the paunch pressed water, so once it's gone through that mechanical separation. And then we also looked at tannery water, which wasn't really viable due to that there's chromium salts in there. And down at the bottom here is what these samples look like after they've mixed and incubated for anaerobic digestion testing. So this is the, I won't dwell on this one too much, but you can see basically that if you're looking at the second from the bottom row, the total COD, you can see that the pig blood, the pig guts, and also the paunch are quite high energy density streams. So basically, all of that available tonnage should be used for anaerobic digestion. The yard manure water, since it was very diluted, it's got quite a low COD, so basically shelve that one. It's not really energy dense enough. And then comparing the Sable overflow with the paunch press water, you can see that they're fairly similar. So what we did, we compared two mixes of paunch water and Sable overflow as a dilution stream. So you'd want to be diluting to around about 10% solids for the anaerobic digester, but also some other general observations with it. The low total solids percentage and COD of the Sable overflow indicates there was a high removal of fats, oils and greases from this stream. So that means it's important to divert the stream before it gets even further diluted by belly wash water or any sort of green stream like that. And as I mentioned, using up all the available tonnage of the blood, guts and paunch. So this is the biochemical methane potential plot that comes out. So you can see that this black trend here is just the solids, so the blood, the guts and the paunch, and it was about 35% solids off the top of my head. Mix 3, which is this red one, is the red stream, is the dilution to 10% solids. And then the purple one here is the paunch press water as the dilution streams 10% solids. So you can see basically that the digestion approach is an asymptote at around about 30 days, which is basically what we'd expect from the literature and most of the industry data suggesting about 28 to 40 days of a retention time. So for a 2,500 meter cube digester, which is a bit of a standard size, you'd be looking at around about a 28-day retention time and a solid loading rate that's really in line with the acceptable the acceptable values in the literature. So the recipe we came up with was for 1 ton of input to the digester, you'd have about 772 litres of paunch water, 65 kilos of guts, 65 kilos of paunch, 130 kilos of guts and 33 kilos of blood. So then we went to the market and got a few proposals. So the first one was the digester. And as I mentioned, you're looking at, say, 2,500 meter cube is a nice sort of standard size, like a nice module. So you've got your digester, your feedstock receiver, which is, and the buffer tank, which is this smaller one here. The digester is obviously the larger one. You've got flare over here and then the civils. Balance of plant, so things like your motor control room and your gantry, etc. So these were generally priced from the market around about $3.5 to $4 million, delivered, installed, and commissioned. And then there's biogas cleaning and the engine as well. So down on the bottom left here, we have an activated matrix of sulfur-consuming bacteria that live on a nice little matrix of wood chips, and they live in this biological scrubber. So the sour biogas is pumped in here, and the sulfur is consumed by the bacteria, and it comes out the top. So every now and then you just might need to change that wood chip matrix over. And then this is the digestion engine here, just a nice standard reciprocating gas engine. So it comes out to around about $2.5 million delivered and installed for these two parts. So the total capex for the digester, the cleanup and the engine, you'd be looking at around about $6 to $6.5 million for this particular scale. We calculated $410,000 per annum in OPEX. So that's mainly in trucking from any sort of outside waste to the abattoir where you're looking to host this plant. And then for this particular one, because as I mentioned, that market for rendered porcine product is dwindling now, this particular one, you could charge quite a bit of a gate fee for those piggery wastes. So it came out to about $1 million per annum in net revenue in thermal energy, electrical energy, reducing your own disposal costs and also taking that gate fee, and then some large generation certificates until 2030. So this worked out to about a 6-year discounted payback period with an NPV over a 25-year life of plant, changing the engine over 15 years for about $20 million and an internal rate of return of 20%. So as I mentioned, delivery cost was the main cost item. So we ran a sensitivity on this one. You can see that even going up, say 50%, it doesn't change the internal rate of return too much. However, the economics were mostly sensitive to those power cost variations, as you can see in here. Say if your power cost that you're able to offset, it drops by half, you're basically losing half of your internal rate of return percentage. So that reflects the scenario of the engine not being able to offset those peak kVAs in the month and along with those kilowatt hours. So what that means in practical terms would be, say if you're not producing on Sunday, but you have a very large kVA spike, whether that be from a large motor coming online unexpectedly or something happens in the refrigeration plant, things like that. So, and then it's also fairly robust against those piggery waste costs dropping down from, say, if you can halve that gate fee to, say, 17% internal rate of return. So overall, the takeaway from that one is gives you good confidence into the future with any sort of changes in market that the plant is still going to be able to operate and making money. And as Matt mentioned, we're looking at expanding to take additional waste. That's the whole point of this aggregated waste to energy. So we considered the local government area food organics, green organics fraction of the municipal solid waste. So this particular plant was in regional New South Wales, where the gate fee, or the landfill levy there is $81.30 per tonne. And for a 20,000 person local government area, we estimated around about 3,100 tonnes per annum of FOGO. And then you start looking at boosting that up with additional businesses, say if there's any sale yards around, any sort of food processing businesses in the local area, grease trap waste from restaurants or any sort of processing like that, and water treatment, things like that. So expanding once you've got that sunken cost of all your civils, expanding, taking another 2,500 metre cube digester and another engine, you're looking at around about $3.2 million with a simple payback, around about 4 years or so. So conclusions on that one. This particular aggregating waste for anaerobic digestion rather than just digesting your own waste, within your own boundary, appears to be an attractive option to offset your costs, reduce emissions, improve energy security, and provide a more sustainable approach to waste management. And as I mentioned, the key figure to lock down is basically what gate fee you can take for outside wastes, and also ensuring your engine delivers the power savings as expected. Just ensure you have no unexpected demand spikes when your engine's not running. So things like check refrigeration plant, any other large motors for direct online starters, or maybe even start delta starters if they're a little bit older. Consider variable speed drives, voltage optimization, and power factor correction if necessary. But I'd assume for most of your processes, they'd probably be pretty good. All right, and now Gareth is going to talk about the biomass boilers.
Good day, everyone. Thanks a lot for your time today and for us to present it to you on these findings. As Max mentioned, anaerobic digesters is a strong opportunity. I'll be talking about boilers, in particular, moving to biomass boilers and looking at what can be done to really drive down the cost of that fuel for the boiler. We flipped it on its head and said, rather than starting with combustible material available at red meat plants such as paunch and how you might dry or pelletize that, to who is burning material that has that high moisture content and is reasonably similar in terms of its mechanical properties to paunch. And the technology that we found comes out of the radiata pine industry, which quite routinely will be burning towards 50, 55, 50% moisture within their green sawdust and green wood chip. And the particular technology, they're designed in New Zealand, takes the fuel into the boiler chamber via a screw and has an understoked fuel pile, high residence time there, and quite thick fibre walls here to retain thermal energy within that system. Secondary combustion chamber there for any fines coming over, and then those hot gases go into your steam drum or your kettle, etc., to raise the steam for the plant. A couple of images here showing you that technology. So moving on to the next slide, one of the critical elements to understand with, say, a natural gas fired boiler is that in the order of 80 to 90% of the cost of running that boiler is the fuel that you put into it, so that capital outlay trends towards being a very low percentage over the life of plant, which is obviously why things like coal have been very popular in the past. So looking at those lower cost fuels, generally those solid fuels are going to be a lot cheaper. And the particular metric to have a like-for-like comparison on fuels is the dollar lower heating value per gigajoule lower heating value. So the dollar per gigajoule of usable heat within that fuel. So with those LPG costs have been up into the low 30s, currently at around sort of the high 20s in terms of dollars per gigajoule. Natural gas has come off the boil a bit, sort of maybe in the mid to low teens, depending on how large a user you are, compared to things like fuel oil, so recycled lube oil. And then moving into biomass, if you get wet, green pine sawdust, there's a lot of moisture in there and a low density. The dollar per gigajoule can be quite high. If you pay for the fuel on a per tonnage basis and have air-dried hardwood chip, there's a lot less moisture. If that wood chip's had 3 to 6 months to dry out, a higher density. So generally, shipment of biomass is limited by the volume that can be held within that B-double truck or road train, for example. And generally, a B-double walking floor is pretty routine. For example, in the Southeast Queensland market, Western Australia might be able to take C trains. So really working with the biomass vendor or supplier to ensure you're procuring a fuel that is suitable for a boiler that is air-dried hardwood chip, rather than something that's more suited to, say, mulching or garden beds, which that wet green or cedar materials might be better suited for. And this is quite an achievable and routine dollar per gigajoule in quite a lot of areas of Australia. Obviously, around that topic of aggregation, looking at fuels that can be free issued, such as paunch, in this case, mechanically pressed paunch in that low 20s in terms of percentage solids, and certainly some of the more recent or advanced mechanical presses are able to achieve closer to that low 50% solids, which means if you are in that sort of a territory, you could consider direct firing of the paunch. If you're starting with that low 20% paunch, you'll be looking at aggregating approximately 1/3 of the tonnage as paunch and approximately 2/3 of the tonnage as hardwood chip, so that you can get the required energy that you need. And the last line there is a very readily available fuel in terms of tonnages, that is refuse derived fuel. So that is the non-compostable, non-recycled part of construction demolition waste or municipal waste. However, you do need to consider the statutory approvals required if you're combusting these sort of mixed waste streams that might have a lot of polymers and other types of material in them. It's certainly an opportunity to generate a gate fee if that was of interest. However, moving on to the next slide, you'll see that after looking at a large number of scenarios, what we have looked at in detail is either a straight up air-dried hardwood chip biomass, and then also that hardwood chip mixed with mechanically pressed paunch to provide an appropriate amount of steam for a red meat processor with a rendering plant. So really looking at things like the moisture, total sulfur, chlorine species, and then those gross net calorific values within these different fuels to arrive at a fuel that's acceptable to the boiler. Moving on to the next slide, you'll see the main parameters that we looked at for these particular boilers. So you can see here in that yellow column, looking at a feedlot in particular, quite a lot of feedlots in regional areas might be utilising LPG. Some are using natural gas. So at that very high dollar per gigajoule for LPG fuel, there's some very strong opportunities there. And if you have a look at the main parameters there, looking at current annual spend, steam requirements, the gigajoules per annum burnt. So then we know the tonnage of biomass and or paunch to swap in. Quite a lot of these boilers don't have economizers, which results in a lower percentage of heat recovered from the fuel. That megawatt thermal rating, which then defines the Capex of the boiler, and wood chip grain wastes in particular for this particular system. There's then the cost of bringing that biomass fuel to site, annual cost savings, and then a simple payback period. So for a 2.5 megawatt boiler, currently using LPG, but then swapping over to a wood chip plus a couple of tonnes of co-created grain waste that's free issued, provides about a 3.2-year payback. Now looking at a red meat processing site, when you compare coal against an existing fully depreciated coal-fired boiler, one of the major motivations that we've seen for moving away from coal is the business continuity risks associated with coal procurement, as there's lower overall interest in thermal coal, but an increasing interest in higher quality metallurgical or coking coal. You're seeing those coal fields moving further north into the Bowen Basin, and those coal mines closer to areas of population density being under pressure. So hence a little bit higher risk there for procuring coal. So moving away from coal is not only economically driven, but in particular business continuity driven. We have excluded carbon dioxide equivalent emissions, so there is no price paid at the moment within Australia. Very roughly, for a say 2.5 megawatt boiler, it might be in the order of a $20,000 cost impost. So a 10 megawatt boiler might be closer towards that 80k. 12 megawatt, depending on usage, might be closer to that 90k as a potential future cost when you look at current emissions reduction fund costs. But we've excluded the cost of any CO2 equivalent emission. However, keeping in mind the targets towards carbon neutrality by 2030, anything using a biomass is considered a biogenic fuel, so there is no carbon dioxide equivalent emissions. There's some very minor nitrous oxide and methane emissions there associated with combustion systems, but fractions of percent compared to say a coal-fired boiler. So process it with coal, say about a $3.375 million Capex for a 12 megawatt rating, taking into account the usage profile, 250 days per annum, 16 hours per operational day, payback period about 11.4 years. So wood chip is able to be procured a little bit cheaper than coal, but then in particular those waste management cost savings associated with paunch. However, once you start comparing, for example, against natural gas, this is where the economics are quite a lot stronger there. So this particular scenario for a 5 megawatt thermal boiler utilising paunch and air-dried hardwood chip, being able to really drive down those annual fuel costs to arrive at a payback period in the order of 2 years. Even better still against LPG. So that was the aggregated biomass boiler scenarios. Within the final report, you'll see a larger number of scenarios run, but these are sort of 3 reasonably typical case studies that we've put forward for that. So moving on to the next slide there.
Just while you're moving on to the next slide, we've got a few questions that have come in, Max and Gareth, so it might be a good time to ask a couple of questions.
Yeah, far away.
Yep.
The first one is to Max. What is the piggery? Yep. Was the piggery a producer or abattoir processor?
Just an abattoir processor.
Excellent. And then the next one was, and I hope I get this terminology correct, what was the SMP of FOGO or GO specifically? What do you estimate to be the carbon mitigation potential of the case study?
As Gareth mentioned with that one, we weren't as concerned with this because of the uncertainty with carbon pricing and that kind of thing. We weren't as concerned with the carbon reduction. It was more about making the economics work.
Great, thanks.
Yeah.
Yep. And the next question that's come through from Murray is, have maintenance costs been factored into the payback figures that you displayed earlier, Max?
Yes, they have. Within the final report, I mean, I don't want to bore everyone with it, but inside the final report, if you are keen on reading into that, there is a big discussion on what those maintenance figures are and the detailed breakdown of the operational costs and the revenues by line.
The next question that's come through is from James, and he has indicated that recent Sydney hub wholesale gas has been down between $4 to $5, leading to delivered prices around $10. Air dried looks good. Have there been any issues post bushfires with supply?
Gareth, you want to take that one?
Yeah, for sure. Yeah, really great question. So when you look at bringing in hardwood chip or sawdust, the aggregated source of that material is normally going to be a sawmilling operation. So, fires do impact the timber industry. However, if there's a fire in a particular region, it will mean then that the state government authorities then release a different asset for harvesting and timber milling. So the tonnages through the timber mills themselves aren't as necessarily dramatically impacted. But yeah, I mean, bushfires overall would certainly have an impact on the overall long-term timber availability. But from what we've seen, there's been other factors impacting the biomass industry. So interestingly, due to COVID, there's been a very high demand for people to do landscaping and having mulch for their own gardens. So things like pine chip, pine sawdust that's quite routinely used for generating compost, cedar, which has a really nice aroma to it and is hence used quite often in that mulching world, has had quite strong demand and reasonably higher dollar per ton costs. Hardwood chip is not as good underfoot. It's not as good for composting, so has a lower opportunity cost. So hence that's the particular fuel, after speaking to a lot of the timber milling guys and with the timber experts, is the preferable fuel for a boiler, because you're not competing with the use of, say, that pine type material or the cedar type material, or the cypress is another good example material. that is more preferentially used for landscaping or composting or things of that nature. I did blush over it as well, but there's other sources of biomass that might be in your area. Cotton gin trash is an example of another large biomass tonnage that may be available for free issue, and clean recycled wood streams. That will come down to the management practices of, for example, the local council or the local landfill, but rather than a refuse-derived fuel, which might have a lot of polymer and plastic in it, via segregation operational activities, you can have reasonably clean recycled construction demolition wood or chipped wood and chipped pallet wood as another fuel, very low cost fuel source as well, possibly from your local council or local landfill. So yeah, long story short, rather than fires, it's actually been activities in terms such as increased demand for landscaping and composting that has driven up prices of certain forms of biomass.
Thanks, Gareth. We've got a few more questions, but we might hold some of these over to so that you can continue on with the presentation.
Yep. It was just a bit more to add. So as I mentioned, yeah, go ahead, Gareth.
Yeah, I was just going to round out the biomass boiler section with conclusions, and then we'll hand back to Max to present on the calculator tool. So obviously, aggregated biomass boilers have the strongest economics when compared against the more expensive fuels. So top of the pops, LPG, secondly, natural gas. And, the question came through, prices have really come off the boil. And yeah, roughly at the user or retail end, the dollar per gigajoule is about twice the transmission cost. And there's some good, clear, publicly available data there, for example, on the Wallumbilla Gas Index and the Victorian Natural Gas Index on the ASX Energies Futures site. So yeah, certainly getting down towards that, back towards $10 and lower teens in terms of dollars per gigajoule for the future, versus things like air-dried hardwood chip in that $3 to $4 range, and then possibly even cheaper sources of fuel again, such as refuse-derived fuel, recycled construction demolition wood, or other ad hoc sources of biomass which might be in your area, such as cotton gin trash or thinnings and trimmings. More modest economics compared to coal. However, there might be other advantages there, such as business continuity improvements. One thing that is very likely, though, is any decision that you make on a boiler or combustion system today will probably be operating within a carbon-constrained world into the future. That is the renewable energy target, the RET scheme around renewable electricity, is concluding at the end of 2030. Some of the pundits are saying that'll probably be replaced by an emissions reduction fund type scheme, or there could be some sort of a carbon trading or some sort of carbon tax environment into the future. So something to keep in mind, that any decision made on a combustion device today will probably be in a carbon constrained world at some time in its life. Key improvement in porch utilisation is to reduce that moisture content. So if you are interested in these multi-fuel aggregated biomass boilers, maybe checking the moisture content of your paunch and looking at getting closer to that best practice 50% solids, as opposed to, say, the 20 or low 20%. That'll certainly help improve the use of that paunch as a fuel, not only getting rid of the water, but it also makes materials handling and shifting of that material, such as by the use of algas and screws, a lot easier. And you can do some smart things around backloading of trucks with paunch from that processor back to the feedlot if the feedlot is the place where that biomass aggregated boiler is being installed. Great. So I'll just hand back over to Max now, who will talk through the calculator that's been created off the back of these works.
Yeah, so as I mentioned at the start, we've got this aggregated waste to energy tool, which will shortly be available on the AMPC website. So you can use this tool for an idea of what waste you're producing and what's the energy content of those, and how does that translate to what are your options. So the red text cells I'll go through in a second are these key inputs, and then basically the cost benefit analysis is presented at the bottom with very conservative estimates, because we realize that we're trying to keep this user experience pretty simple. So try to keep it as streamlined as possible. So I'll drag this one over. And hopefully that'll show. And we'll just run through a little demo. So say, for example, if we're running through, say, 6,000 head per week at an average of 355 carcass kilos per head. So you're looking at, say, 2,130 tons of standard carcass weight per week. So based on all of our previous jobs that we've completed, these are the estimated waste production volumes and an estimated solids percentage. But if any of these are greatly inaccurate for your own site, you can change these. So say, for example, let's change this one to say 200 tons per week of paunch, and maybe there's a little bit lower green stream screenings, maybe it's only 5, for example. And then I'll go through and I'll show the effect of this local council population in a minute. The next one we have down here is what are your waste to energy options. So as I said, we've got anaerobic digestion, gasification, and combustion of paunch and wood in a 1-to-1 ratio, just to hit that target of 50% solids if you can. 50% moisture if you can, that Gareth was talking about. So this has got a little bit of info on what kind of tonnage would be going through each individual technology, and what are the recoverable electrical offsets in megawatt of electrical and megawatts thermal for each particular one. So, and then we'd also put in a little bit more cost data for our site. So let's say 14 cents a kilowatt hour. In this one, the power demand price is in $1 per kVA per day. If you happen to be billed on $1 per kVA per month, you can just multiply or divide by 30. So let's say for this one, it's around about 27 cents per kVA per day. And say we're burning natural gas at $12 a gigajoule, let's say. So this graph down the bottom here will populate. So we have anaerobic digestion, you're looking at around about 6.5 million, net revenue around of say 700,000, and a simple payback of 9 years. Gasification, as I mentioned, is pretty expensive technology. So you either need to have very, very expensive power or gas or thermal fuel that you're offsetting, or you have to have a hell of a lot of waste going through it. And then paunch combustion as well. So this is a little graph here, and I'll just show the effect of what taking some of that local government area waste would do. So let's say we have a 20,000 person local government area. You can see the effect that might halve the anaerobic digestion simple payback. So it's definitely handy, to take some of those outside wastes if you can. Really boost up your own production. Boost up your own processing of those aggregated wastes to help along the viability of your waste to energy plant. So were there any questions on this one? It will be available on the AMPC website shortly, but if there's any specific questions right now, I'd be happy to run through those.
So we've got a few more generalized questions, Max, that have come through. So I might ask you a couple now. What quantity of wastewater would be processed by the 2,500 cubic meter module per day? And that's come from Taz.
Per day, let me go back to my okay, you can calculate this one. I'm not sure off the top of my head, but This one had a solid loading rate of 3.3 kilograms per meter cube per day at a 9.5% total solids percentage and a 28-day hydraulic retention time. So, you know, there's not a huge volume going through per day. It depends on, you know, what kind of head per day is currently being processed. But for this particular site, it was around about 1,000 head per day, and it wasn't the existing wastewater treatment plant, so the save all and the screens needed to stay around. It wasn't taking all of that. It was taking probably about a third of the save all water, I believe.
Great, thanks for that. And
I just ran some quick calcs in the background there. You know, roughly, depending on how well attuned the bugs are to that particular feed and the mixing that's going on, you know, you'd anticipate maybe 60 tonnes per day. However, as those bugs become acclimatized to the particular feed, you're able to start to push up the solids concentration, the volatile solids per cubic meter per day rate. And so you might be able to get up closer to that sort of 80, 83 tonne per day.
thanks for that. The next question, which is a follow-on question from the earlier question that Peter asked, was, Max, could you give a bit more information around the specific methane potential, the SMP, of FOGO and GO used in your calculations?
Yes. So that's an interesting point. I'll go through to this one. So this table of test results here, as I mentioned, that basically we infer the value of the biochemical methane potential from this COD. However, it's not exactly transferable. So generally you'll find, as you can see in this graph here, that the performance of the co-digested feedstock might not add up as the sum of the parts due to this. It's around about 40,000 reactions that are actually happening between the hydrolysis and the methanogenesis, the methane production. So it's very complex interreactions between those two, between those feedstocks when you're looking at how does the recipe perform greater than the sum of the parts. What was the second part, sorry, Amanda, about the carbon potential?
So, yeah, what do you estimate to be the carbon mitigation potential of the case study?
Carbon mitigation potential of the case study.
What we might be able to do with Peter after.
We have run some numbers in the past comparing a open anaerobic pond with a covered anaerobic lagoon, where that biogas is used to offset scope 1 and scope 2 emissions. So scope 1 being the boiler emissions, scope 2 being electricity that's brought to site. So if that's a topic of interest, we can definitely calc that out and include it in the final report, which is going to be released pretty soon. As you could well imagine, the lion's share of carbon dioxide equivalent emission savings is due to removing the fugitive emission of that methane into the air if it's an uncovered anaerobic pond. The comparative CO2 equivalent emission savings for the boiler fuel and the electricity is a much smaller percentage compared to the fugitive methane emissions. So hence the argument for putting on a flare. It's very good from a safety perspective and odor management perspective, but also by the combustion of methane in the presence of oxygen being converted into CO2, you're reducing the global warming potential of the gases that are emitted. So it's an advantage. We have done those calcs, so we can certainly include it, seeing it's an area of interest.
That'd be great. Thanks, Gareth.
We will
And
contact us at the end. So if you just send us an email, we can send that to you. We can cut that out and reply to you, Peter.
And the last question that we've currently got is, have you considered including dewatered sludge, digestate, or for combustion? What would be the minimum moisture request?
Yeah, really good question. So if you look at these understoked heat pile burners, moisture target or solids percentage target of 50-55% solids or higher. So the parts that you're putting into the boiler fuel is not that important compared to that the final mixture ensures that it has a solids percent, a lower heating value, and then other contaminants such as chloride, and fluoride, and heavy metal levels below the acceptable level. So certainly things like dewatered WAS sludge could be mixed in, but there's a bit of a tipping point there between having something that with effectively a negative lower heating value, such as what you'd see with a WAS type sludge or a wastewater treatment plant sludge, versus a positive lower heating value with paunch. When paunch is at that sort of 21-22% solids, it does actually have a positive lower heating value. And then if you can get it up towards that 50% solids, the lower heating value improves again. So you could certainly include it, but WAS is quite an interesting sort of mixture. As you know, it's biological. It really wants to hold on to that water. You can run it through a high-speed centrifuge and it'll still retain, 80% plus water in it. So it is a more difficult material to dewater compared to the paunch material. Punchline being, you can definitely include it, but most WAS type sludges will have a negative lower heating value. That is, you're putting more energy into boiling that water off than what is obtained from combusting those constituent parts, which means you're having to go and buy more wood chip and add more wood chip in to manage that sludge. So for those thermodynamic reasons, it wasn't recommended as a boiler fuel.
Great, thanks, Gareth. That's all the questions we've currently got. So I'll hand back over to Max.
Well, that was all I had to say on the tool. As I mentioned, it will be available on the AMPC website shortly. So jump on there, have a play. Even send us an email if you've got any major suggestions or comments on it, any improvements you think. But yeah, just jump on there, see the effect of diverting some of your non-recyclable waste to energy. Maybe even do a few what-if scenarios with your cost data. Say, what if my power tariff changes and I start paying more for kilowatt hours versus kVAs, or if I change my fuel from, say, LPG to natural gas, how will that affect the viability of anaerobic digestion and cogeneration, for example? And then also talk, if the effect of the local council population taking that waste is very great, I'd suggest, start maybe having discussions with some of those adjacent businesses in the area. If your local council is particularly amenable to these waste to energy projects, get in touch with them. But that was all I had to say on that one. Yeah, and that's the end. So those are contact details there. If anyone had any major questions that they think up later, just send us an email there, info@allenergypl.com.au, or you can check us out online at allenergypl.com.au, or we're on LinkedIn as well. So thanks for having us, everybody.
Thanks, Max. There's been one more question come through from Mohammed. In the tool, can we use MSW as feed?
Yes, that's the idea of filling in that number.
Fantastic, thank you.
So as feed for what? Waste to energy? Yep.
I would believe
That's
so.
the idea. So we've done the local council on local councils and local government areas and correlating production of municipal solid waste, the FOGO and the RDF to a population number. So if you can put in, say, in my local government area, I've got 10,000 people, 20,000 people, 30,000 people, whatever, and you can easily find that number online. And then that will help bolster that tons per week digested or tons per week burned or gasified, and then have that effect on the economic step in that graph at the bottom.
Perfect. Thanks, Max. I'd just like to take the opportunity to thank everyone that joined today's webinar. We had a really good attendance today, some fantastic questions, and a big thanks to Gareth and Max for taking the time to do your presentation and answering all those quite difficult questions, a couple of them I thought, but some really good questions, which is great to see. And I think, you know, the outcomes of this project have been fantastic to be able to sort of review and see where the industry can take them and use different waste options as well, which has been great. So if anyone's got any further questions or anything like that, please reach out to either Max, Gareth or Matt Deegan from AMPC. Once you've had a bit of a play with the tool, I'm sure Matt Deegan would love to hear your feedback on if there's any sort of changes, improvements or any additions that AMPC could consider moving forward as well. So thanks everyone. I just want to shout out that next week's webinar, we're doing a complete different change of focus, and we've got a safety webinar around bullying, harassment and your safety obligations. So some information will come out on that later this afternoon. So once again, thanks everyone for attending, and we'll catch up with you all soon.
Thanks, Max and Gareth.
Thanks, Matt.
No problem, Matt. Cheers.